So far we have learned about normal strain. Here we want to focus on shear strain. Consider this beam which is subjected to a force. We have learned that there are basically two kinds of stresses developed in this beam: normal stress and shear stress. The force acting on the beam causes deformation. So consider this is the beam after deformation. The element which is subjected to normal stress deforms like this. The element stretches because of the applied tension stress acting on that. This is what we have defined as normal strain. So normal strain is caused by normal stress. Similar to that, we want to determine what kind of deformation caused by shear stress. Let's think about it. What kind of deformation do you expect to see when the element is subjected to shear stress? Do we expect to see any sort of elongation or contraction in the element? Generally, is there any change in the length of the element? No. The deformation caused by shear stress is like this. As we see, the top surface slides compared to the bottom surface. If we look at this deformed element in details, there's not any change in the length of the element at all. But what is changing is the angle. So consider point O in this figure. Before applying the load, before applying the stresses, the angle was pi over 2. It was a right angle. But after applying the load, the angle decreased to theta. Here, the change in the angle is defined as shear strain. So general definition of shear strain is intensity of change in the angle of the element. Let's define that here. If the top surface slides by the value of delta x, and if the length of the element perpendicular to that slide is L, we can define gamma or shear strain as delta x over L. Note that there is a difference between the delta and L used for determining shear strain as opposed to the definition that we had before for normal strain. In shear strain, delta x is perpendicular to the length L. But in normal strain, as we can see in this figure, delta is parallel to the initial length of the element. This equation is actually valid when deformations are very small. Generally, in most cases, it's easier to calculate directly how much is the change in the angle of the deformed element after applying the load using trigonometric equations. We will talk about that in details in several problems later on. Strain is a unitless parameter, so similar to normal strain, shear strain is a unitless parameter, and it doesn't matter if it's SI unit or US customary unit, we can just use radian for that. So radian is just a number. But generally, as I said, shear strain values are very small, so it's easier to work with microradian instead of radian, which is basically 10 to the minus 6th radian. The next things to be considered here is the sign convention. We need to define what is positive shear strain and what is negative shear strain. Consider this element which is deformed after applying the shear stresses. The positive value for the shear strain means that the angle between the axes x and y decreases in the deformed object. Similarly, the negative shear strain means that the angle increases after applying the deformation. It is a bit odd because we usually think that increase should be related to positive sign and decrease should be related to negative sign, but this is the sign convention that we have for shear strain in mechanics of materials. So again, if the deformed angle decreases from the initial angle, we call that as positive shear strain, and if the deformed angle increases compared to the initial angle, we call that as negative shear strain. Note that we don't define shear strain as the angle after deformation. The shear strain is not the angle that is shown here. This is the angle of the element after deformation. Shear strain is actually defined as the change in the angle. So let me show it here. Look at this angle and this angle. Let me call it gamma 1 and gamma 2. Shear strain is gamma 1 plus gamma 2. So we need to see how much is the change in the angle from the initial angle at that point. Let's talk about an example to learn the concept better. A thin rectangular plate is uniformly deformed as shown. Determine the shear strain at P. Assume that delta 1 is 1/16 inch and delta 2 is 1/8 inch. Alright, to determine the shear strain, we need to see how much is the change in the angle. How much is the initial angle at corner P in the original element? That's the right corner. The angle is pi over 2. And we need to see how much is the change in the angle after deformation. To determine that, we may note that point Q moved up by the value of delta 1, so there is a change in the angle because of that movement. Let's call that change in the angle as gamma 1, and point R moved to the right by the value of delta 2, and that causes another change in the angle. Let's call that gamma 2, and if we know how much is gamma 1 and gamma 2, we can determine how much is the overall change in the angle of the element at that point. So let's focus on how to calculate gamma 1 and gamma 2. Let's focus on calculating gamma 1. To determine gamma 1, we can form a triangle. Tangent of gamma 1 is delta 1 over 25 inch. So let me write it down here. So tangent of gamma 1 is equal to delta 1 over 25 inch. That means that I can determine gamma 1 as inverse tangent of delta 1 over 25 inch. Delta 1 in this case is 1/16 inch, and if I plug the value, that gives us 0.0025 radian. Similar to that, we can determine how much is the change in the angle caused by movement of point R to the right by the value of delta 2. Tangent of gamma 2 in this case will be delta 2 divided by 42 inch, or gamma 2 is equal to inverse tangent of delta 2 over 42 inch. Delta 2 is 1/8 inch, and gamma 2 will be equal to 0.002976 radian. Alright, we have determined the change in the angle at corner P. One caused by delta 1, another caused by delta 2. Now, listen carefully. How much is the overall change in the angle at that corner? That would be simply gamma 1 plus gamma 2. So that will be the overall change, which is equal to the shear strain. So shear strain at that corner is equal to gamma 1 plus gamma 2. And if I add the values together, that gives us 0.005476 radian. And as I said, this strain is very small, and it's better to convert it into microradian by multiplying that by 1 million, and that would be equal to 5476 microradian. That's the answer of this problem. Alright, there is a notification here. There is one important fact here. Here, for determining gamma 1 and gamma 2, we used inverse tangent. But it is not necessary, actually. We don't need to use inverse tangent to determine how much is gamma 1 and gamma 2. So in this case, instead of determining gamma 1 as inverse tangent of 1/16 over 25, if I simply divide 1/16 by 25, I will get the same number. It's because gamma 1 in this case is equal to inverse tangent of gamma 1, or I can say it's equal to inverse sine of gamma 1. Similar to that, the same is true for gamma 2. So gamma 2 is equal to inverse tangent of gamma 2, or inverse sine of gamma 2. Why this is true? Because gamma 1 and gamma 2 are very small, but this is not the case for all problems. In some cases, angles are larger. Let's solve another problem to see how we can deal with that case. A thin polymer plate PQR is deformed such that corner Q is displayed downward by 1/16 inch to a new position Q as shown in figure. So assume that there is a force acting at that point Q which pulls down that triangle and causes deformation by the value of 1/16 inch downward, like this. Okay? The question asks, determine the shear strain at Q associated with the two edges PQ and QR. So it basically asks how much is the value of shear strain at that corner Q prime. Let's look at this triangle in detail. How much is the initial angle at point Q, at corner Q, before applying the load? It's 90 degrees. Okay, it's pi over 2. How much is the angle after applying the load in the dashed element, in the deformed element? We can determine that. How we can determine that? Let's consider this. Let's consider the right triangle. Can we determine how much is alpha 1 in this triangle? Yes, we can. Tangent of alpha 1 in this case is the front edge, which is 20 inch, divided by the side edge, which is 25 inch and 1/16. Okay? So we can determine how much is alpha 1. Similar to that, we can determine the angle on this side, alpha 2, in this triangle. And the new angle after deformation is called alpha. Okay? So shear strain here can be defined as the difference between the initial angle, which is pi over 2, and the new angle after deformation, which is alpha. Shear strain, which is shown by gamma, is equal to pi over 2 minus alpha. And let's do the calculation and determine how much is alpha. Tangent of alpha 1, as we discussed, is 20 inch divided by 25 plus 1/16 inch. Look at this triangle for detail. So tangent of alpha 1 is 20 inch front edge divided by the side edge, which is 25 plus 1/16 inch. Alpha 1 would be equal to the inverse tangent of 20 over 25 plus 1/16, and that would be equal to 0.673523 radian. Alright, we can do the same for alpha 2. For alpha 2, tangent of alpha 2 in the left triangle is equal to 31.25 inch divided by 25 plus 1/16 inch. So alpha 2 is equal to 0.894837 radian, and I can determine shear strain from this equation. Gamma is the initial angle, which is pi over 2, minus the new angle, which is alpha 1 plus alpha 2. We will get this number. There are two important notes here. First, in this case, pi over 2 and alpha are very close to each other. So in calculating the shear stress, we are subtracting two close numbers from each other. And in that case, we need to use more significant digits than usual because there will be round-off error. And if we don't use more significant digits, we may end up with wrong numbers. This is actually, I can say, the only case in mechanics of materials that we need to use probably 6, 7, or 8 significant digits in our calculation. And the reason is that because we are subtracting two close numbers. But in other calculation in mechanics of materials, we can work with 3 or 4 digits, and those should be sufficient, and they will give us accurate results, but not in this case. The second important notes that I have here is calculation of alpha 1 and alpha 2. In this case, I can't say alpha 1 is equal to tangent of alpha 1. Okay? Similar to that, we can't say alpha 2 is equal to tangent of alpha 2. Why? The reason is alpha 1 and alpha 2 are not small. So as opposed to what we had here, where gamma 1 was equal to tangent, inverse tangent of gamma 1 or tangent of gamma 1, here in this case, we can't say alpha 1 is equal to tangent of alpha 1. The reason is, in this problem, alpha 1 and alpha 2 are large, and in this problem, gamma 1 and gamma 2 were very small. So, to be on the safe side, always use inverse tangent or inverse sine to calculate the angles. Another example. This example actually combines shear strain and normal strain. Due to the loading, the plate is deformed into a dashed shape shown in the figure. Determine A, the average normal strain along the side AD, B, the average shear strain in plate at A relative to the x and y axis, C, the average shear strain in the plate at B relative to the x and y axis. Let's focus on part A. The normal strain along the side AD is defined as the change in the length of that part divided by the initial length. So let's call that delta AD divided by LAD. LAD is the initial length of that side, and delta AD stands for the change in the length of that. Alright, how much is the change in the length of that side? The new length is AD prime, which is 13 inch. And the initial length is AD, which is 12 inch. So I can define the change in the length as AD prime minus AD. And how much is the initial length? That's AD. So I can define strain, the normal strain, as AD prime minus AD divided by AD in this case. The new length of the element after deformation along the side AD is 13 inch, and the initial length was 12 inch, and that gives us 1 over 12, which is equal to 0.0833 strain. Alright, now let's calculate shear strain at A. Shear strain at A is defined as the change in the angle at that side. The initial angle is pi over 2, it's 90 degrees, and the angle increased after deformation. We can directly determine how much is the angle after deformation. Look at this triangle. In this triangle, sine of gamma A is equal to 2 inch divided by 13 inch. And we can determine gamma A as inverse sine of 2 over 13, which would be equal to 0.1545 radian. Okay? And here I use the negative sign for shear strain. Why I use negative sign? Look at corner A. In that corner, the angle increased after deformation. And based on the sign convention that we had for shear strain, which is shown here, if the angle increases after deformation, we call that negative. So here I used negative sign for showing the angle at that point. Alright? So that is answer of part B. For determining answer of part C, we don't need to do any calculation because the overall change in the angle at that corner is equal to gamma A. So I can say gamma B is equal to gamma A. But I should note that gamma B has different sign. Look at that. Look at corner B. The angle at corner B decreased from 90 degrees, decreased from pi over 2. So that would be positive sign. So I can say that gamma B is negative of gamma A to be correct with the sign. So the angle at that point would be positive 0.1545 radian. And that would be answer of part C. Alright, let's quickly review these three problems that we discussed. In this problem, to determine the shear strain, we directly determined the change in the angle. We used trigonometric equation. This is similar to the very first problem that we discussed. In this case, we were able to determine the change in the angle directly. So we have determined gamma or shear strain directly by measuring the change in the angle. In this problem, we didn't directly measure the change in the angle, but what we did was we determined the angle of the formed element at that corner, then we subtracted it from the initial angle. So basically there are two ways to determine the shear strain. One way is to determine the angle of the element after deformation and subtract it from the initial angle to see how much is the change in the angle, which is shear strain. And sometimes, as in this case, we can directly measure how much is the change in the angle. Alright, there are other problems related to shear strain. I would recommend you to review them and practice by solving more problems to understand the concept better.